Welcome, everybody. This conference is the sort of first one at Hong Kong UST. And we're happy to be sponsored by a number of agencies, in particular the Swissnex China, and Hong Kong UST, and IAS. I would like to introduce the Hong Kong UST President, Tony Chan, to say a few words to welcome you.
Welcome, everybody. I understand some of you have visited Hong Kong, and in particular HKUST before, but some of you probably have not. So welcome here to HKUST and to Hong Kong. This event, as you just heard from Henry, is part of a sort of several-month-long event, sort of Einstein in Hong Kong. I was at the inauguration of that. Now, that's kind of a double meaning. I mean, obviously, cosmology, Einstein. Now we're having this conference in Hong Kong, so that's part of it. But I don't know how many of you know Einstein was in Hong Kong twice, actually. In fact, the first time he was here, he got the news that he won the Nobel Prize. He was actually on his way from Hong Kong to Shanghai, and there were no wireless communication then, so he got the news when he landed. Well, no air. I think he was on a ship when he got to Shanghai, and the Swedish consulate informed him. That's what we were told. We're very happy to be co-sponsoring, co-organizing this several-month-long event with many of the agencies. You saw them here, in particular the Swiss consulate and also SwissX, the Croucher Foundation, and the Lee Hazen Foundation. So these are some of the major sponsors of scientific enterprises in Hong Kong. This event is particularly important to us in many respects. First, it is part of the celebratory events of our 20th anniversary. So we are only 20 years old. If you had been here, some of you probably had been here 20 years ago, this was just some green field or brown field, literally dirt everywhere. This place was supposed to be an army barrack, over here, or film studio, depending on who owns this place, who's using the place at the time. And, 20 years is a very short period of time for research university. But through the effort of our staff, our predecessors, I think we feel we have come some way. We have a long way to go. The latest news was exactly a week ago. We were ranked by some place that we're #1 university in Asia, if you believe it. We believe it, of course, when they say we're #1. Okay, so that's an important event, a milestone for us. It's also important for us because of our upstart IAS, our Institute for Advanced Study, which you'll hear a little bit more about that this afternoon when we inaugurate our new director, Henry, who just came a few months ago. But I thought for this audience, most of you are physicists or in related disciplines, the idea of an IAS, I think, need no introduction, really. I mean, we're talking about Einstein. I should learn how to say that properly. Of course, he spent part of his career in an IAS. Our next speaker, our distinguished speaker, David Gross, is heading an institute I know a lot about, KITP. Even though, these two are not, we're not exact copies of that. I would say, fair enough, both institutions are inspiration for us, a role model for us. So we'll see where we'll go. So it's an important event for us, too, from that perspective. Now, coming back to the science, I worked in I'm a mathematician, a computer scientist, so, I really have no right to know much about cosmology. But I worked at the U.S. National Science Foundation for a few years, in which, during that time, I worked a bit with distinguished cosmologists, string theorists like David and other people. To me, it's a fascinating subject. It really is really at the frontiers of science. I mean, I think what you guys try to do is try to, answer both fundamental, big and small questions. big and small, meaning, you're talking about the cosmos, and now you're talking about the smallest particles in the universe. Here I see in the talks you have, you're talking about the LHC, you're talking about dark energy, and, I think especially for the non-scientific field, I think this excitement, this sort of convergence of ideas, I think should be transmitted to the public as much as possible. I think that's, in a way, David's general talk today is a step in that direction. Okay, so I understand you have people coming from all over the world, from many, many countries, and we welcome you, but we also see that actually UST, we aspire to be a gathering place, a marketplace of intellectual ideas, a platform for gatherings like this. We want to continue this in the foreseeable future. We want to welcome you back. You can spread the news if you like what you see here and bring back your colleagues and so on. And finally, today, it's a beautiful day. I just came back from a trip. The last 2 days were not as nice. So don't spend all your time inside this room. Go out, enjoy the spectacular setting of our campus and also Hong Kong itself, exciting city. So welcome again.
Thank you, Tony. I'm Gary Hsu, chair of this morning session, and it is my distinct pleasure to introduce to you the first plenary speaker of this conference. Professor David Gross really requires no introduction. As you all know, he was awarded the 2004 Nobel Prize in Physics for his work on asymptotic freedom, the theory that underlies the strong interactions, one of the 4 fundamental forces of nature. But more importantly, he was the first, hopefully not the last, string theorist to have been awarded this honor. So, in addition to the talk that he's giving today, David would also be giving a public lecture on Wednesday. Since this morning session is really tight, I will save more formal introductions for the public lecture. So today, David will share with us his perspective of cosmology. And without much further ado, please join me in welcoming Professor Gross.
Thank you. Thank you for the introduction, and thanks, Tony, for your remarks, and Henry. It really is a great pleasure to be back here at HKUST, where I visited, I think, twice before. One very memorable occasion about 2.5 years ago when I gave the commencement address here while my house was almost burning down in Santa Barbara. Luckily, I only found out after the ceremony was over. Didn't burn down, so it all worked out. This is a beautiful campus, a very ambitious campus, coming from an only slightly older campus, UCSB, which has gone quite far in a short amount of time. I'm especially full of admiration for what HKUST has managed to do in just 20 years. Amazing. And I'm delighted that you founded an institute of advanced studies, or an institute, we'll see what it turns out to be, and under the leadership of one of our own, Henry Tai, who will do great things, I have no doubt. So this is an exciting occasion, and I was asked to give some opening remarks, which I will proceed to do. This is really a collection of remarks about cosmology and string theory. And I start out just by apologizing to those in the audience who have heard some of these views expressed before, sometimes with the same slides. So, when I come to cosmological conferences, unlike particle physics or even string theory, I must say my first feeling is envy. Cosmology in the last few decades has been an enormously exciting field. This is truly a golden age of cosmology. The title of this conference is something like Cosmology since Einstein. 100 years. When was Einstein's first paper on cosmology? About 100 years ago. And in a sense, as a physical science, cosmology didn't truly exist before Einstein. So everything we've learned has been learned in the last 100 years, and most of it in the last 20 years. And the observational ability of astrophysicists and cosmologists, or the growth in their ability to do actual quantitative observations of the physical characteristics and the history of the universe, is truly mind-boggling. I can't think of another science where the advances have been so rapid and so profound. And as a consequence, there's been an actual theory called, as usual, as we call it in particle physics, a model, but it's approaching a theory which works very well and is a marvelous triumph of this century of physical cosmology. Cosmologists and particle physicists and string theorists share a lot in common. In the famous cube of theory space, where we plot theories as they fit in to a metaphysical space whose coordinates are the three fundamental dimensionful parameters of nature, Planck's constant, which tells us how quantum a phenomena is, velocity of light, which tells us how relativistic it is, or Newton's constant, which tells us how much geometry responds to mass and energy. In this space, most of physics lies on this axis here. It's called condensed matter physics. You have a non-relativistic, non-gravitational world, which is, however, full of absolutely fascinating quantum structure, and, of course, which determines everything we see in this room, including ourselves. But once you turn on once you turn on relativistic effects, and even more so when you turn on gravity, things become much more complicated and interesting in a way. Particle physics is located on this face of the cube where gravity can be ignored. It is an extraordinarily weak force inside the atom and the nucleus, as you know. In my generation, particle physicists took general relativity as a fun course in graduate school, never hoping to have to really understand it. General relativity, on the other hand, Einstein's theory of gravity and its application to cosmology, by and large ignores quantum mechanics, and so it lies on this face. This center of the cube, the whole thing, however, is required when you want to do string theory, or, for that matter, cosmology nowadays. So string theory and cosmology share that common ambition or disease that they can't turn off any of these parameters except in, as limiting cases. And both are faced with the challenge of constructing, understanding a situation in which both quantum mechanics, general relativity, gravity, and relativistic effects are important. And they clearly, as we have learned, need each other. Cosmology clearly needs something like string theory because it is beginning, with its great successes, to push back towards regimes where quantum gravitational effects become relevant or strong, back to the Big Bang, to the beginning. The very successful theory of inflation, or inflationary paradigm, needs string theory for a variety of reasons, but for sure to justify its often ad hoc or fine-tuned constructions, which are made in the context of theories that we know break down when we push back towards the beginning. String theory needs cosmology partly to make contact with observation. It is a truism that we often repeat that particle accelerators allow us to probe directly back to the Big Bang, but they don't get that far or to those high enough temperatures or energies. The universe, however, did, we believe, and maybe we can see signals of that. More importantly, string theory needs cosmology to provide the challenges that might reveal the secrets of the theory, which we are far from understanding. Those challenges, which are the driving force of any science, in the case of string theory, are unfortunately not coming that much from experiment. But they can and are coming from the challenges of helping cosmology push back to the Big Bang and understand the past or the future. Well, what could we actually do for cosmology? What can fundamental physics do for cosmology? So these are a few of the things that one can imagine it doing. In fact, that string theory is doing at the moment. String theory can provide cosmology with new tools and new mechanisms that really don't fit in easily to the standard theoretical framework of quantum field theory and effective field theory. Branes, extra dimensions, and they can provide, for example, new models of inflation. They can challenge the point of view that naive effective field theory models exhaust all the possibilities, and that's important in doing comparisons with experiment and with keeping an open mind. And most important, perhaps, or eventually, they can provide new perspectives on the actual beginning of the universe, which we're driven to try to understand, and for which simpler techniques of quantum field theory, effective field theory, are clearly inadequate. Now, the standard model of cosmology, which I'm sure will be reviewed by someone here with the latest high precision numbers, really works remarkably well. I would say better than anyone expected at this point in time. It is built on the inflationary paradigm of a period of very rapid expansion in the early history of the universe. But in addition, it has revealed two so far invisible features of nature that are crucial for understanding the structure of the universe and of great interest to particle physicists and string theorists, namely dark matter, which we infer but don't see, and so-called dark energy, or the cosmological constant. It's really amazing how much of our knowledge or our concepts of what exists in the universe and in our theories is invisible. We have invisible matter, invisible energy, invisible quantum dimensions, invisible extra bosonic dimensions, invisible unification, invisible constituents of space and time. I mean, we have both direct evidence and lots of speculation about lots of stuff we haven't directly seen. Nonetheless, we proceed with a confidence built on past success of physics. After all, our predecessors, like Mr. Einstein there, I like this picture because Einstein's pictured not as this old man with flowing hair, but sort of in his 40s, or very dapper. He confirmed the existence of atoms theoretically. And remember, atoms were invented by theorists to explain thermodynamics, to give a statistical mechanics basis for the laws of thermodynamics, to explain the behavior of atoms. Behavior of atoms explain chemistry and chemical reactions, Brownian motion. Who would have believed that that invisible stuff, which was the basis for the theoretical understanding of matter, would today be seen? You know, where you actually see atoms in modern microscopes. You can even spell out IBM by placing individual atoms of cobalt at given positions. So, you know, the reason we're able to construct our understanding of the universe and speculate about all these invisible things is that we have confidence that everything we talk about eventually will be seen, even though we can't imagine today how that will happen. So I'll discuss some of the invisible components of the universe and of our theories. And let's start with dark matter, which is the one kind of matter that I think was, that was discovered not by particle physicists in laboratories on Earth, but by astronomers trying to understand the motion of stars and clusters of galaxies. And it's certainly there, and it's probably there in the form of heavy particles, weakly interacting massive particles. Now, that has posed an enormous challenge for the last decade or two to particle physicists who should have discovered it first. But now that it has been discovered, it is really the job of particle physics to produce it. Now, theorists have no problem. Almost any new physics beyond the standard model produces new, heavy, perhaps stable particles. And the reason also kind of explains why we haven't seen them so far in the laboratory. And that's because if they have standard model couplings, then you require masses in the GV to TV regime to explain the density of such new weakly interacting matter, dark matter in the universe. So the numbers do work out. You could work backwards from the given abundance that astronomers produce and standard model lore to predict that where they should have been seen is where we're just about starting to explore, with great power, both in underground detection experiments and at the LHC, where we hope to produce them. Now, of course, particle physicists were looking for them at much lower masses because they always underestimate where to look. But it's not really a surprise that we haven't yet seen or produced dark matter. What is kind of likely is that we will see it very soon. It could come from some kind of new particle like this. It also could come from axions. There are other possible explanations of dark matter. By far the one that appeals to me and relates to one of our profound conjectures with no visible evidence is supersymmetry. Supersymmetry is, of course, the purported symmetry of superspace, which is a purely theoretical construction for which there's no direct evidence, namely the hypothesis that in addition to ordinary space and its symmetries, say rotational symmetry of ordinary space-time, there exists a bigger space which contains new kinds of dimensions, quantum-ish dimensions, whose coordinates do not commute. And as we learned, now almost 40 years ago, there is a beautiful mathematical generalization, a beautiful mathematical framework, which remarkably was discovered by physicists and not mathematicians, in which ordinary spaces fit with extra anti-commuting Grassmannian coordinates. These spaces are natural extensions of ordinary space-time, and the symmetries of ordinary space, such as the Lorentz symmetry of flat space, have a beautiful extension to supersymmetries of superspace, in which we can also rotate ordinary coordinates to supercoordinates. The appealing thing of this larger framework in which one could do physics, not just space-time, but super space-time, is that it relates bosons and fermions, the two kinds of particles that exist in nature for profound reasons in a quantum mechanical relativistic description of nature, one into another simply by rotating in superspace. Now, this theoretical extension of standard physics is quite remarkable because, as it turns out, just about any theory we've ever constructed has a natural extension into superspace. And any field theory that describes bosons, say in ordinary space, can be extended to a theory describing both bosons and fermions in superspace. So one can do this with any theory, and this was done early in the history of supersymmetry. And of course, if you rotate a boson, get a fermion, and you didn't have it before, you get a new particle. You predict new particles. Any field that depends on bosonic coordinates when embedded into superspace has an extra supercoordinate, theta, which, since it anti-commutes with itself, theta squared is 0. So the Taylor expansion has the original bosonic field plus a new field psi, which, since this is anti-commuting and this is commuting, this must be anti-commuting, namely a fermion field. Now, the particle physicists who developed this theory in the 70s tried to apply it to the real world, and problem was, of course, how to reconcile the doubling of particles, that exists because of this simple rotation of bosons into fermions and vice versa. In the standard model, where the matter is made out of fermionic quarks and electrons, and the force carriers are bosons, photons, Ws, gluons. Supersymmetrizing the standard model, which is easy enough, leads to a doubling of the particles and new particles we never saw before. However, symmetries that are not manifest in the world around us by the 70s were already commonplace. And so it's no big deal to explain this away by saying that these particles are simply too heavy. And supersymmetry is not a manifest symmetry. It's not a symmetry of the ground state of nature, of the vacuum. And therefore, this mass splitting is okay, even though the laws of physics are invariant under supersymmetric transformations. If supersymmetry is in fact broken at a scale, an energy scale of a TeV, then these particles, these new particles, we haven't seen because they weigh about a TeV, or in that range. Now, at the time supersymmetry was being developed, it was as speculative as anything is in physics. There were a few attempts to explain the neutrino, right, as the partner of the photon, and that's why it's massless, which of course it isn't, and it doesn't work anyway. But it was, it was fun games. The clues that convinced me to take bets, even odds bets, which I'm willing to take with anyone after this is over, on the discovery of supersymmetry at the LHC in the next 10 years, is not based on this beautiful structure and also the fact that it's an inherent crucial part of string theory, but rather the following three clues which came up over the years after the theory had been discovered and worked out, and which people realized, supersymmetry can solve that problem. And they are, of course, the unification issue, the fact that extrapolating the forces of the standard model sort of unifies with but not exactly with high precision. But if you supersymmetrize the standard model, the unification is extremely good, to about 1% after 14 orders of magnitude of extrapolation. This unification of the subatomic forces could be an accident, could be a coincidence, or it could be evidence for unification, of course, and supersymmetry, which brings these three lines together with a breaking at the scale of about a TeV. If you really believe in unification, you better take this clue seriously. And that is a strong clue, in my opinion, for supersymmetry at a TeV. Then there's the theoretical issue of small numbers, the mass hierarchy, the so-called hierarchy, which is the relation between the scale of the electroweak force and the unification or Planck scale, which is a very small number. We know how to explain a lot of small numbers. To explain this one is easy if you invoke supersymmetry. And again, that to reproduce the electroweak scale, you need breaking at about a TeV. And then finally, a candidate for dark matter, which is what I was talking about. It's a natural consequence, generically, of supersymmetric models, that they have discrete symmetries that predict a stable neutral particle, which could very well be at a TeV, and if so, would have standard model couplings and lead to the observed density. It doesn't predict the mass, of course. So that is another clue, in my opinion, that suggests that supersymmetry is to be discovered. Low energies, 1 TeV we now call low energies. The evidence from astrophysics, as in this bullet cluster, is overwhelming. So 3 coincidences or 3 profound clues. Well, here's where we'll find out. And in the talk today, Peter will tell us. At least when, not. So this would be an incredible triumph of all of these different invisible theoretical ideas and experimental observations of the structure of mass throughout the universe to end up with the discovery of supersymmetry, which I remind you, I always like to emphasize, is truly profound because it truly means that there are quantum dimensions of space and time. It really means that to the extent that the arena for describing the physical universe is x, y, z, and time, you have to add theta 1, theta 2, as many as you need. The fact that symmetry is broken doesn't mean that that isn't the right description of the world. Just like the fact that, in this room, rotational symmetry is broken doesn't mean that there aren't x, y, and z, and that the laws of physics are invariant under rotations. So there are perhaps to soon be discovered quantum dimensions of space and time. Well, what about the other dark thing, which has been misnamed dark energy? Should be dark pressure. I mean, what has been, again, discovered, measured by experimentalists, is the acceleration of the universe at one of the largest scales, very large scales. And that acceleration, of course, is due to the negative pressure and not the invisible energy. There is a default, of course, namely the cosmological constant. So my view on dark energy is that, well, it's obvious what it is. There's no mystery about dark energy pressure. It is the cosmological constant, which is forced on us by general covariance and our modern understanding of quantum mechanics. So if you go back and read Einstein's original paper, which I always urge my students to do, read the original papers. Actually, Einstein's papers on general relativity had a whole bunch, but when he finally knew he had it, he wrote a paper which was beautiful, which he argues general covariance, and then he writes down the most general Lagrangian, except that's not how he did it. He wrote down the most general field equations, which involve only second derivatives with respect to time. He didn't want ghosts or violations of unitarity. So anyway, he knew the problems you get into if you have higher derivatives. And that led him to Einstein's equations. Now, he realized shortly after that there was another term that was allowed by these general principles. Those were the only principles he had. And he realized that when he was trying to construct the first cosmological model of the universe, which had to be consistent with observation, and observation told him that the universe was static. And he also had Mach's principles around. So he had two which he was trying to, whatever Mach's principle was, he was trying to be consistent with it. And so he realized there was another allowed term, which is either geometrical, comes from varying the volume term in the Lagrangian, or could regard it as a form of matter, which is the way it's presented as dark energy now. Pervasive form of matter and pressure that pervades the universe. This way of thinking about it, of course, then with a modern point of view, after quantum mechanics, it's clear that even if you don't put it in, such a term will be produced by quantum dynamics. Another way of saying this is in effective field theory, you write down, consistent with the symmetries of the theory, the most general action in terms of local terms, the dominant term at large distances in the infrared, of course, is the volume of the universe. The second next term, the Einstein action, Hilbert action, is the curvature. And there are curvature squared terms, and so on. This volume term dominates in the infrared, which is why it will dominate the final history of the universe, if things are as bad as they look. Einstein's curvature term we're quite familiar with. Higher order terms we haven't yet seen directly. They're not so relevant in the infrared. And in principle, by our present standards of understanding in quantum field theory, there could be an infinite, probably are, number of such terms, all of whose coefficients are arbitrary, except the scale is set by the Planck scale. So to say that this is special compared to this is absurd from this point of view. They're exactly, in fact, you might say the opposite. This one is, why do we have this one? Now, of course, if we just had the volume, there are no derivatives. It's a little thicker. But there are two parameters here, or more precisely the ratio of these two parameters. That is a bit bizarre, namely the value of the cosmological constant. But that has nothing to do with the nature of dark energy. That's simply a number, which theorists should understand, of course. And it is hard to understand. Now, this is a problem of what the value of the cosmological constant has been around for a long time, and theorists have screwed up on this one in more ways than is possible to enumerate. Starting with Einstein. So Einstein famously introduced the cosmological constant to create a static universe. And then when he learned that that was unstable, and that, more importantly, Hubble had discovered the expansion, after arguing with de Sitter in a very interesting correspondence, de Sitter claiming that that expansion was the Sitter expansion, and Einstein arguing, no, it isn't, the cosmological constant got a bad name. And Einstein was famously quoted, and I tried to find out where this quote came from, that introducing the cosmological constant was the greatest blunder he ever made. You know, he never says that in print anywhere. I did discover an attribution of that remark to Gamow, who claimed that Einstein said that. I think Gamow, because Gamow was well aware of what I'm coming to next, namely quantum fluctuations produced an enormous cosmological constant. And he probably didn't like the cosmological constant. But what Einstein probably was saying was, if I just followed my nose, I would have predicted the expansion of the universe if I hadn't been stuck on these preconceptions of Mach's principle and a static universe. So that was Einstein's greatest blunder. And in a way it was, Albert. You know, that would have been the greatest prediction of all times. Imagine you start with a principle of equivalence and you predict the universe's expanding. And Einstein missed it. Now, any theoretical physicist would agree that's a blunder, and Einstein was man enough to admit that, but he never said that, therefore, it shouldn't be there. And in a letter, he says, one of his letters to de Sitter at a lot of arguments, he said, well, future generation, it's obviously, at the moment you can't tell whether it's there, you need it or you don't. Future generations will measure it. Now, quantum physicists, however, got very disturbed when they realized that, you know, the quantum fluctuations in the vacuum, this is a picture from QCD of what's going on in the vacuum at the scale of a nucleon. That's what the vacuum looks like. Those things have energy, and the scale of energy is a GeV. So quantum physicists like Gamow realized very early on that, you know, in quantum mechanics you're going to produce energy in the vacuum and negative pressure, whatever you do. Can't help it. And of course, the answer they got was infinite, because these theories had ultraviolet divergences. And so the second big mistake of theorists was something's infinite, must be zero. This was the prevailing point of view when this was first discovered. There were a lot of infinities. The electron mass was infinite. Everything you calculated quantum mechanical corrections to in relativistic theories was infinite. And it wasn't just the cosmological constant that was thought to be infinite. The corrections to Dirac's equation were thought to be zero as well for a long time, till they too were measured and led to renormalization theory. So if something is infinite, it should be zero, which is possible. There could be some principle. Now, in the 80s, we began to have serious theories of string theory, of quantum gravity, in which it wasn't infinite anymore. It was calculable. But, of course, it came out, just as you would expect, back of the envelope calculations to be enormous, because these fluctuations occur at all scales and produce energy at all scales up to the highest. So now it became a real problem. You can't say something is zero because it's obviously not infinite, so there must be some reason it's zero. Now it's just big, but very big. So people again said, well, it must be zero. There must be some reason, and searched for the reason. So I first learned about supersymmetry in the halls of CERN in 1974, when Wes and Zumino were working out supersymmetry for field theories. And I remember running into Bruno Zumino in the hall, and he was very excited because he had just realized that supersymmetric theories, cosmological constant, is zero. And that's the only mechanism we've ever found that produces zero. Now, it didn't take Bruno long, maybe the next day, to realize that's not going to help you because supersymmetry is broken. We don't see the photino, the selectron. So when it's broken, all that does is reduce it by 60 orders of magnitude. Again, we kept saying, okay, well, there's some reason, some symmetry, some anomaly forces it to be zero. Still might be the case. Haven't found it, though. So again, theorists really screwed up here. And they convinced the astrophysicists and the cosmologists that it had to be zero, because these guys, they trusted these theorists. And at the time the cosmic acceleration was being discovered, which is an interesting history, these guys were extremely uncomfortable because all the people they respected and listened to were telling them that you better find zero, better find zero. Well, it doesn't seem to be zero. At least there seems to be cosmic acceleration, exactly what a non-zero vacuum energy and negative pressure produces. The equation of state, the ratio of pressure to energy has been measured to 10%, agreeing with cosmological constant. And of course, in hindsight, well, what else did you expect? So there's really no mystery here, except the only mystery is, how do theorists screw up all the time? I mean, why? But, however, there is this extremely small number. And that has bothered a lot of people and led to all sorts of ideas, like the landscape of possible vacua or universes with different laws and different cosmological constants. And the reason we're in one of them is simply that if we weren't, we wouldn't be asking the question, namely the entropic principle. Now, this might be true, but I think the arguments for it are very weak, and the conclusion, or especially the attempts to turn a circumstance like this into science, are quite unfortunate. But the conclusion, which is based on essentially two principal assumptions, namely that there are lots of possible universes within which the parameters, for example, the cosmological constant, that are crucial for the emergence of structure in the universe and life, that is very unlikely, rare, and that there exist large number of universes where a parameter like that varies almost continuously, and a mechanism that populates this ensemble of universes. Then you might come to the conclusion that if all those are true, are the case, that we would end up with an exceedingly small value of the cosmological constant because we're there to ask the question and we have no chance of calculating it, and who knows what else goes along with it in this one universe that we can observe. However, I think most of the assumptions that go into this conclusion are very shaky. The landscape is a landscape of things that really only are discussed in effective field theory. They're metastable states at best, and they're not consistent as solutions of whatever it is we're trying to solve because they do not give consistent cosmologies. The mechanism of internal inflation and tunneling between vacua, the very notion of a multiverse of causally disconnected pieces of something, are technically and conceptually shaky, to say the least. But I think the biggest problem is the fact that the tools we have to address these questions, and the best tool we have so far is what's called string theory, is also in a rather technically and conceptually shaky position. Here the main problem is we don't really know what string theory is. And we're continually discovering new aspects of, new ways of looking at it, but we still don't really know what string theory is. Is it a theory where you write down equations with well-defined rules? Does it have a Hamiltonian, a Lagrangian? Well, it certainly isn't anything like that. It's, at best, some kind of new framework that incorporates, as far as we can tell, ordinary field theory as well. And we're not sure what its boundaries are. We're not sure exactly, as I said, what it is missing to make it a theory. What picks out one of the quantum states that string theory gives you solutions of from another one. We have indeed a vast landscape of string theories or of formulations. Some people argue that every point in that landscape is a different theory. Well, we certainly have a vast landscape of formulations of string theory, some of which are traditional string theories, which start out with classical string propagating in some background to which you add quantum effects, some of which start out, some of our best definitions of corners of string theory start out as familiar field theories one uses in the standard model. QCD is somewhere in this. We don't know exactly the string theory description yet, but there's no question that it has one. Supersymmetric quantum mechanics with no space at all, no gravity, just quantum mechanics of matrices. Only time is a string theory, is in the same framework, landscape. These are all related by various dualities, continuous transformations. But what is this? What is it? A framework which you choose a particular member of which to be a theory, like you choose QCD out of the realm of quantum field theory, whereas QCD is actually embedded in this much bigger thing? We don't know. It looks like any consistent field theory is in this game as well. So string theory is never going to kill string theory, by the way, because its standard model is connected to string theory. Everything is string theory. It gives it its power, but it also tells us it's only a step on the way to the ultimate truth. The power of the relation between simple quantum states or simple solutions. I hate to say the word solutions of string theory because I don't know what the equations are. But the quantum states one constructs with the prescriptions or techniques of string theory that describe some limit strings moving in ADS negatively curved space and contain supergravity or Einstein's equations as an approximation as being dual to ordinary four-dimensional gauge theories has given this insight enormous power, because you can use Einstein's equations to learn about gauge theories. You can understand, conversely, the behavior of black holes and the resolution of the information paradox by using ordinary gauge theories. Calculate transport coefficients of the quark-gluon field using string theory, as well as perhaps learn about quantum phase transitions in strongly correlated electron systems. So the framework has enormous power, but we still don't know what the theory is. So we're missing something, clearly. It's very difficult to talk about what one is missing and what one has no idea what it is. But you can definitely point to places which the missing ingredients are probably truly required. And a lot of them have to do with cosmology. For example, there are a lot of solutions of string theory, as far as one could tell, are perfectly mathematically well-defined. And where we even have a way of doing physics. We know what observables are, we know what experiments would be, we know everything. And they're perfect. They have gravity, they have everything. They're just not the real world. Highly supersymmetric, flat, asymptotically flat spaces. There are an infinite number of such theories. It's a bigger landscape than the de Sitter landscape. The de Sitter landscape, one that looks like cosmologically like our own universe, at least for some time, isn't really a solution because it's singular if you extrapolate it to the past, maybe to the future. So even in picking out a solution of string theory or a quantum description, a quantum state using the techniques of string theory, the one place we've actually completely failed is to do that for worlds that look like our own, and maybe there's some principle that would pick out a unique solution. I don't know. But the real issue, I think, has to do with space-time, where we have many, many indications and growing that there's a different way of thinking about space-time. The classical notion of a smooth manifold truly fails in many ways. Even the notion of a fixed dimension of space doesn't make sense because we can change that as we vary parameters continuously. Topology, the same reason. We can change topology continuously in string theory. We have much evidence that there are best descriptions of string theory states constructed in quantum states constructed in string theory, are through formulations where space and therefore gravity is emergent. Could it be that all of space and time, that our most basic concept of the universe is an emergent concept. It's very hard to deal with that problem because all the examples we have are really of emergent space, not time. Time is hard to fool around with. Let's try to imagine physics with more than one dimension of time. And how do you formulate the rules of physics if you don't start with something like time, or space-time? And then finally, coming back to cosmology, what are the rules? So the universe, as Einstein taught us, isn't the question is not the question that particle physicists used to pose. What does the universe look like now? What is the universe? What are the basic particles and forces that exist in this room now, and I can predict experiments tomorrow? The question is the whole space-time history. That's the answer to the question, and that includes the beginning, the boundaries of the universe, if there are any, in the end. So it's not about describing the state now, the whole thing. Of course, if you really describe the state now, you would be describing the whole thing. And the problems with those vacua now is that if you extrapolate them back in time, the beginning is totally singular. Well, this kind of question that Einstein first asked, and truly in a scientific way, what is the universe, the structure of the universe, the space-time history, the whole thing? So it's a very young question for physics, and it clearly was not a question that anybody really dreamed of answering until recently. And string theory certainly has given us some confidence in giving us a consistent quantum theory of gravity that we have the tools to answer such a question. But in my opinion, we only have some of the tools. And the reason we don't have all the tools is that we've never truly had to answer that question before. So physics sometimes gets these kinds of questions where you're not sure what the answer could be, what the nature of the answer is, and you don't know what the rules are. In the case of the universe, you're not even sure what the observables are in many situations. You certainly don't know what the rules are. Well, that is a problem and a challenge, to be sure. But let me come back to a simpler challenge and end with that. Can we explain this number? Or is it a clue that something truly profound is going on, like the entropic nightmare? Well, what is the problem? The real problem is the ratio of what we might expect given supersymmetry, which will be discovered soon. Now, this is a ratio of energy density, so we should take the fourth root to make it a more conventional ratio of masses, and it's a very small number. Or if you invert it, it's a very large number. Now, Dirac in 1937 was the first person to worry about large numbers in a cosmological setting. He asked how many protons are there in the universe, and what is the size of the universe compared to the size of the atom. And he ended up with about 4 ratios, all of which were 10 to the 80, or when you take the fourth root, 10 to the 20, big numbers, like the mass of the proton compared to the Planck mass. 10 to the minus 19, even smaller number than the cosmological constant. And Dirac could have invoked the entropic argument. He could have said, if this number was 1 or 1,000th, then it wouldn't have been such a mystery. We might have been able to calculate it. But then we wouldn't be here because put together 1,000 protons, they'd form a black hole. This is the number that tells us that gravity is so weak at the scale of protons by 40 orders of magnitude. So entropically, this number has to be very, very small. Otherwise, macromolecules, people can't exist. But Dirac didn't invoke anthropic arguments. They'd been around before him, but I don't think he thought very much of them. Instead, he said, okay, I can't calculate. I don't know enough. But I could relate all these numbers, like the ratio of the size of the universe to the size of the atom. That varies because the size of the universe grows and the atom doesn't, unless alpha, say, varies with time. So he predicted the time variation of the fine structure constant on cosmological scales and of Newton's constant, and that you could measure over the years, and has ruled out Dirac's theory of the equality of all these large numbers in the universe. But this number we understand. And I like this argument because this came from QCD. This was solved by QCD, indeed by its feature of asymptotic freedom. So the physics behind it is very simple. If you start with a reasonable, standard coupling, fine structure constant, whatever, at the unification scale, which is where the mass, the Planck mass comes in, then what determines the size of the proton? Well, it's the force between the quarks. It's the distance you get to, but when the force between the quarks becomes big, of order 1, where the quarks are then confined. That sets the radius or the mass of the proton. And the reason this number, Dirac's large number, is so big is that the coupling is running logarithmically. So you get this exponential. So the number is very small or very big, but the logarithm is reasonable, and you can estimate the logarithm, and you get it to within an order of magnitude. So you can explain this number 10 to the minus 19 within an order of magnitude as simply coming from the fact that the coupling that determines in the end the mass of the proton, which doesn't depend on the mass of the quarks. It's just the scale at which the quark energies are confined automatically. So we can explain numbers like 10 to the minus 19 easily. Or if you take the fourth power, 10 to the minus 80. And we have other such explanations for what's going on? We have other explanations, a hierarchy problem. Again, if you have supersymmetry, it's the same logarithmic trick. Neutrino masses, we have a seesaw mechanism. We again have 3 very small numbers we've explained in particle physics, which is quite amazing. So the problem is not that this is so small. That's, we've seen many times. The problem is simply we have no idea what the mechanism is. That's the problem. Neither did Dirac. He couldn't have, in 1937, explained the proton mass in terms of the Planck mass. But personally, I think it's likely, the story is much more likely to repeat itself. We will find the mechanism and explain it and calculate it as we have before. So the standard model of cosmology works beautifully. It has produced a beautiful theory of inflation. It has confirmed the discovery of these invisible components of the universe that probe, that challenge experiment and theory. And in the coming decade, we're going to have a lot of very high precision measurements, observations that will test this theory in ways that are truly, in very strong ways, and perhaps with sensitivity to Planck scale physics, where we might touch the questions raised by string theory. In the case of dark matter, we're very likely to both detect and produce dark matter particles and to measure their properties and discover supersymmetry. So that's for sure in the next decade. But will we understand the value of lambda? Will we understand the nature of space and time? Will we understand the rules of quantum cosmology? Well, that I'm not so sure. But we can hope. So I'll just end with a final comment by Einstein, who would have been, I'm sure, both very proud and very perplexed to sit at this conference 100 years later. Thank you.
Thank you, David, for such a wonderful talk.